Welcome back to Elements of Chemistry tutorials. Today we're going to continue our discussion of electron configuration, but we're going to talk about the abbreviated configuration, exceptions, and ions, all the little details that complete it. So abbreviated configurations are used when the electron configuration is so long that it's confusing. So we abbreviate the configuration by naming the previous noble gas in square brackets and then the rest of the configuration. No, you can't do krypton by just putting Kr in square brackets. To do krypton, you would have to do argon and then the rest of the configuration. It's always the previous noble gas. So let's find barium. Barium is right here on the periodic table. Oops, let me get my pen to work here. Right here on the periodic table. So we look at its previous noble gas is xenon. So we'd put xenon in square brackets and then start with that 6s2 level. Let's pick another one that would be rather more problematic. Let's do something in the F block because those are a little trickier. Let's do this one right here, PR. PR is element praseodymium. So we're going to look at what its previous noble gas is. This would be fitting in this square right here. So its previous noble gas is also xenon. So for PR, we would start with xenon and then start over with the new row, 6s2. We've got to step on that 5d1 spot before we can go for F2. So the F block's a little tricky. Let's do another one in the F block. Let's do one of my more favorite ones here, berkelium. Okay, to do berkelium, let me clean this up so we're not getting confused by what's there. Berkelium's in the last row. So our previous noble gas is here at radon. So if we do BK, we're going to start with Rn in square brackets. That's the previous noble gas. And we're going to start here at 7s2. We're going to go to 6d1. And then in our 5f, we're going to count over 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've also talked about F block and we've talked about noble gas configurations. Remember, we cannot do radon by just putting radon in square brackets. Students always have little problems on tests, especially in multiple choice. That'll always be one of your choices, but don't do that. It's not a good idea. Okay, it's moving on. So there are also some exceptions to the rule. Remember earlier we said that having a full sublevel was the most stable configuration. And if you can't be full, you want to be half full. So for example, beryllium is more stable than lithium because it has an S2 configuration. The most stable for that row would be neon because that's the noble gas configuration. The most stable is having your S and P sublevels completely full. So we look at where halfway are. In the P's, halfway are here in the nitrogen family. And yes, nitrogen is more stable than oxygen. We pack snack foods under nitrogen to prevent them from going rancid because if there was oxygen in there, it would make things oxidize. So the D is where you're going to generally see it. And the problem people or elements, I anthropomorphize too much, are the ones they want to be full. So here's copper and silver. They are so close to being full. They just need one more electron to be full. How do they do it? They take from the S to promote it up to the D. Same thing happens at D4s. These D4s are going to take from the S to promote to be a D5. Because if you can't be full, you want to be half full. Remember, half full, let's look at what's going on. Here's chromium. It's got one empty orbital with nothing sitting in it. So it's going to take an electron here from calcium and promote that electron up so that it's going to be a 4s1 3d5 instead of a 4s2 3d4. This just increases the stability of the atom. There are a few other elements that do this promotion that aren't at that D4 that are at a D3 or one of the other configurations. And these are those important catalyst metals. But let's look at what it looks like in an orbital diagram. So let's go look and do silver. Silver is one that promotes. Silver is sitting here with 47 electrons. Okay, so this is going to take us some time. Our S is going to be full. One in each orbital. We pair them up. Remember, we put one in each of these d orbitals before we pair it up. Okay. Now I'm going to look at just what's going on for silver. We have this electron right here, this S1. In silver, we are doing little half arrows here. That's the silver's normal configuration. It's going to be, if we look at it as a noble gas configuration, it would be krypton, 5s2, 4d9. But this little electron right here is going to get bounced up, and it's going to fill in that spot right here. So silver is really going to be krypton, 5s2, 4d10. Okay, so what happens when we have an ion? We've talked about exceptions, but ions. Ions are atoms that have gained or lost electrons from the valence shell. Remember, our valence shell is our outermost S and P. So let's look at calcium. Ca plus 2. If we look at calcium, normal neutral calcium is going to have 20 protons, so 20 positive charges, 20 negative charges, 20 electrons, so it is electrically neutral. But if calcium wants to be stable, it's going to lose 2 electrons. Let's look at it here. Calcium's got 20 electrons. Let's put them in. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. You'll notice I'm drawing little half arrows. You see that often. 19, 20. There's calcium normal. But to be stable, it wants its outermost S and P full. Well, that occurs back here. So these 2 electrons are going to go away. Now we're going to have 20 protons, 20 positive charges, but we've only got 18 electrons. That gives us that a plus 2 charge. Oxygen 2 minus. We know it has gained electrons because electrons are a negative charge, so the overall charge is going to be negative. Why did it do that? Well, oxygen has 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. See how it's got 2 spots here? If it can take in 2 electrons, it's going to have that noble gas configuration of neon. That is much more stable. It has 2 extra electrons than protons. It had 8 protons, but now it has 10 electrons. So it's got an overall -2 or 2 minus charge. Where do these electrons come from? Well, that's going to be an answer that we're going to talk about in bonding. In bonding, you'll see that generally atoms form ions. Now, don't look at these noble gases. They're just here to give you a placement on the periodic table. The fluorines, this group 17, next to the noble gases, they all form -1 ions. Why? They're 1 away from full, so they want to take in an electron. So negative charge. This oxygen family, they're 2 away from full, so they want to take in 2 electrons. This nitrogen family, they're 3 away from full, so they want to take in 3 electrons. As a general rule, metals want to lose, nonmetals want to gain. If you haven't gotten this far in your periodic table yet, there's a zigzag line that runs through the periodic table that separates the nonmetals from the metals. So we have anything in the first family, which we refer to as the alkali metals, they want to lose that one electron. If they lose that one electron, they're going to back up here and look like a noble gas. The second family, they want to lose two because they want to back up to look like a noble gas. These transition metals in the middle have multiple ways that they can get there. Some only do one thing, like silver only loses one, zinc only loses two, cadmium only loses two. But look here at copper. It can lose one or it can lose two. Nickel is generally a +2, but it can be also a 4. Also, some of these, what we call other metals down under here, they do multiple things. Here's lead. Lead can be a +2 or a +4, depending on how it bonds. And we'll talk about that in our next unit, bonding and nomenclature. And just the ions give you a general hint of how things are going to bond. Fluorine wants to gain an electron, and gee, look, lithium wants to lose one. So lithium fluoride is a common chemical compound. Just a little preview of what's to come. I hope you had a great day. Have a wonderful tomorrow. Stay kind. Be safe.